Good morning, everyone. I'm Avinaya Tripathi, a PhD student at Arizona State University, working under the guidance of Professor Narayan. I'm going to present to you about a self-strength sensing kind of mix that we made based on from iron. So, initially, to give the background, sustainability-wise, we have been trying to cut off replace cement by different replacing agents, and even in the process itself we are trying to cut down carbon. One process is to replace cement with fibers and particulates. So here we are trying to incorporate a metallic iron powder that is like a waste product from steel manufacturing. So these powders are accumulated by an electric arc furnace in the process of production of steel, and these are very hard to reuse or recycle, and they are traditionally just dumped into landfills. And why not use it for some usefulness in concrete? So one way we can cut down the carbon from the cement is by basically carbonation of metals. And here the basic theme was to use these iron powders to make the concrete transmittive, so that we can most probably use it to sense strengths. But again, initially we have to characterize the mechanical properties. So what we did was we tried two different types of mix. One is alkali activated slag mix and another is a normal OPC concrete mix. So we basically added 10, 20 and 30% by volume of iron powders into the mix and checked for their compressive strength and flexure strength on 28th day. So you can see the iron particles are nearly in the range of the particle size for OPC, and there is little to no change in the compressive strength. You could say there is a slight decrease, but again it's not as significant. Flexural wise, there is a slight increase on the strength of the mix. So at least the incorporation of these powders into the mix is not showing any negative effect into the mechanical properties. So now, based on this, we moved forward with the mix from 0 to 40%. I'll mostly show based on 40% what we got. So this 40% volume of iron powder was mixed into the concrete, and small beam specimens were prepared, where we attach electrodes onto both ends of it, insulate it with tape, and we had a flexure test setup that was connected to the impedance spectroscope. So what we did was we did stepwise loading, so that we have certain stress induced into the beam and see if we can measure the resistance of the beam to figure out the strengths on the sample. So initial observations are again, with iron powder being conductive, the resistance of the mix with more percentage decrease from the OPC paste, and the decrease is significant for 40%, 10, 20, 30% lying in between these two. So another observation you can see is for different stress states, for the OPC paste, the impedance and resistance you see are kind of cluttered together. They are not as separate to distinguish between the different states. While for a higher iron powder content, the differences are quite significant, which we'll see later with different form factors also. So this is a general AC dependent frequency measurement for the resistance that we do. And so the consideration on this is basically we are considering that the percolation threshold is reached, because these are in the range of 10, 20, 30, 40% of replacement. We are assuming that the percolation threshold is reached. We are not trying to figure out what changes the percolation threshold. And so with the percolation threshold reached, what would happen is let's say the specimen goes through tension. So the conductive material, the iron powder will separate apart from each other, resulting on a reduction of the resistance. So when we put flexural stress on the beam, the measurement that we get from the impedance spectroscope, we are assuming it to be tension, and it's a safe assumption because the compression side will not have a resistance, will have a resistance different from the tension, and tension will be the one that we observed in the results. And yeah. So based on this, we also developed an electric equivalent circuit that we use for understanding the response. This will come back later again. So for the fractional change in resistance, so here like we compared, this one has all the different ratios. So we compared the stress state with the delta R by R naught. So R naught is the initial resistance of the mix when there is no stress applied onto it, and delta R basically is the difference that we see from the initial state to the stress state. So you can see that when there is no iron powder incorporated into the mix, the change is very low, even with higher stress. And as the percentage of iron powder increases, the differences keep on increasing and they are quite significant. And this again is a tensile stress that we are plotting this against. The sample that was tested on was a wet sample. It was not dried because we wanted water to be there for the conduction medium through the pores too. And so basically based on the stress state and the delta R by R naught, we can, based on the general flexural equation, we saw the strengths that were induced into the samples, and we plotted that against the delta R by R naught that we saw. For OPC, it's more or less flat, while for a 40% it's quite significant. So how this translates is, at a point of time, we introduced another factor called gauge factor, that basically is the ratio of delta R by R naught divided by the strength percentage. So the more the form factor, the more significant response we see on a small strength change. So you see a higher delta R based on a very small strength change. What it helps to do is like basically you don't have to be too accurate enough. You have to basically kind of change it to the strength. Like you will see even smaller strength changes based on a higher percentage of iron powder. And another observation was like again based on other studies that are based on carbon fibers and steel fibers, these form factors were quite significant. Sorry, gauge factor were quite significant. So again after the experimental result, we wanted to model it to kind of see the replication of the results on a model, and the consideration were that it was considered that the microstructure is heterogeneous and this makes the modeling complex because now it's like iron powders embedded into the concrete matrix. So how do we change that? Basically make that better. We had to introduce a interface in between these mixes such that we introduced a 5 micrometer interface between the powder and the concrete, which helps it transfer the properties from a concrete to the iron powder kind of linearly. So coal fit were done based on the results to obtain the parameters required for these equations, and we see that we could, based on two different parameters, permittivity and conductivity, we were able to see similar parameters for the fit. And for the general modeling, what we did was like we took some optical microscopy of the cross section, and all the materials that we see here, the iron powders, we basically made an equivalent volume proportion of the iron powder as an elliptical section covered by another 5 micrometer elliptical section acting as an interface. So the thing we observed is like when we acted a stress upon it, now the model was acted on by mechanical load. We saw that the sudden change from again in the interface also caused the model to have voids and see stray currents on the section. So what we had to do is like introduce cohesive zone parameters. This again was obtained from a different study that gave us the KIC values, the fracture parameters for the interfaces between the iron powder and the matrix, and non-existing thickness. Basically, a zero thickness cohesive zone was introduced in between the interface and the concrete to model this. So, again, this is the debonding thing that I told you had the problem with occurrence. And once the cohesive zone was introduced, again it was based on a certain percentage volume. What we did was like for 0, 10, 20, 30, 40, all the percentage, we kept the parameters similar, and we saw that the pseudo thickness basically considered, the value considered for the cohesive zone did not need to change in between these different percentages. And when these models were compared to against the experimental results shown by the triangular hollow ones versus the different hertz. So here the consideration is 100 kilohertz is required to reach a constant delta R by R naught. So as you increase the thing from 100 kilohertz to up, it does not change significantly. So we saw that the model with cohesive zone was able to quite closely predict what we got experimentally. The result without cohesive zone is not shown here. That was not able to predict this quite closely. So conclusion of the thing being, like, again, a percentage of 40 up to 40% of iron powder also did not show significant reduction. At least with flexure it showed improvement in the flexural strength, while for compression it was not a significant decrease. This embedded iron powder itself could give us a strength state. Again, initially the gauge factors for the thing need to be figured out, but once that's figured out, you could use this system inherently itself to get the stress states from the strain stress that is facing at the point of test. And a model was developed based on this with cohesive zone and interlayers, which could replicate the delta R by R naught values that we got. I will like to thank NSF for the funding of the project, and thank you everyone.